So this is a vector. We can determine its properties. Great, now what? How can we rotate it, stretch it, reflect it, or any other manipulation with it? Sure, we can stretch it by multiplying it with a scalar like we learned last time, but is there a more elegant way to write a transformation for more vectors? Like functions being more elegant way of getting a result from formulas? Well, yeah, we can do it with a matrix. Not the matrix, but a matrix. So welcome to lecture 33, the last lecture of our math chapter, matrices. Also, on the bottom of the slide is a website called 3dgauss.com. It's great for visualization of matrices, what they do and how to break them down into linear equations. So if you're studying alone, I recommend this site. It's quite useful for visual learners. So we know how to write vectors, right? Either the vector equals to the brackets thingy, or we break it out into components where each unit vector, so this one representing x direction and this one representing y direction, is extended for their x and y components, respectively. So basically these are two ways to write a vector like we learned last time. But there is another way, and that is with a matrix. So put the square brackets and then the components like this, or this one is more commonly used for programming and stuff like that, but we will be using this one, so the vertical version. But yeah, this is basically how you write a vector as a matrix. So what even is a matrix as a concept? What does it mean? Well, it's a spreadsheet, basically. Like we see on the representative image, we can have n columns and m rows. For example, a 2x1 matrix or 2x3, like we see here. First you count the rows and then you count the columns, and that's the dimension. So as I will show you later, a 2x3 matrix would basically be 2 rows and 3 columns, of course, with the square brackets around them. Kind of like that. The important part here is that we don't multiply these two numbers, so a 3x2 matrix is labeled like this, because this is not equal to 2x3. Sorry, this is a weird cross. So these two are not equal. Just pretend this is an x here, because I cannot draw for shit. But yeah, next we see that inside the matrix we have elements, and they're named entries. So think of a matrix as a structured collection of numbers or values, just like a vector is a structured collection of its directional components, I guess. Also important to note, because I'll get into it later, each position of an element has its own coordinates, so they're encoded just like the dimension state. So first you say the row, and then you say the column. So a position of an element 3, 2 is in the third row and second column. This is going to be useful later, so it's recommended that you remember this. So first is the rows and then is the columns. So remember, when labeling the dimensions of a matrix, always look at how many rows there are and then how many columns there are. So how long is it downwards and then how wide is it to the right. For instance, this is how you would write a matrix. Now, because this is a very hard to write way, because this is, I think, a table of elements that I put the square brackets around, so it's a little bit more spaced out. Takes a lot more time than just writing out an equation. So because I'm on PowerPoint, I'll be using this, the equation form, so it will be slightly more compact. But yes, this is a 2x3 matrix, as it goes 2 down and 3 to the right, as opposed to a 3x2 matrix that goes 3 down and 2 to the right. So these two are not the same. This is important. Now, why did I mention vectors? Well, vectors can be represented by a 2x1 matrix, or sometimes 1x2, but that's for programming, so most of the times it's gonna be like this, where x is above and y is under. This is super useful, as when we learn rules of computation with matrices, we can fit vectors right in, just like any other matrix would be used. Because, well, yeah. And that's how you also transform vectors, because matrices just define the transformation on the vector or other matrices. So if we extend this rule to unit vectors, we see that unit vectors I, so the one for the x direction, and the vector j for y direction, vector I is this. It has a value of 1, 0, because it moves 1 along the x-axis and 0 along the y-axis. So its representation would be 1, 0. For j is the other way around, because it goes up for 1 unit and 0 towards the right. So kind of like this. It's just one more example to reinforce this knowledge into your minds. Now, for the rules of computation, for matrix addition, we need to make sure of something. That something is the same dimensions. So if we have a 2 by 1 matrix, we can only add a 2 by 1 matrix to it. So the number of columns has to be the same. Sorry, this is the rows. So number of rows has to be the same, and the number of columns has to be the same. So of the two matrices. So M1 has to equal to M2, and N1 has to equal to N2. This is the basic rule for addition. Now, when you remember those coordinates, when we had like that, and A3, 2, etc., well, a coordinate in the resulting matrix. Why is this important? Because when you add two matrices together, like vectors, so a 2 by 1, so something here, something here, something here, something here, in the result, this will be added to this, and they will occupy the first slot here. And this will be added to this, so they will be like this, and we will have a 2 by 1 matrix as a result. So the resulting coordinate, so let's say at random place 5, 4, when I is 5, the result in the resulting matrix, so the element in this resulting matrix, will be equal to the sum of the elements of the matrix A at the same position plus the element of the matrix B at the same position. We see that I value is the rows, yes, and J value is the columns. So A12 is first row, second column. And to add together two matrices, we add up the elements in the same position, as I said before, and then the result is placed on that position. So something like this. We have A11 in the first row, first column. So in the resulting matrix, in the first row, first column, A1 will be used as a part of the result. So we're going to look at the first row, first column in the B matrix and add this element to the first row, first column of the resulting matrix, kind of like this. So just to solve an example, a very easy addition would be like this. 1, 2, 3, 4 plus 5, 6, 7, 8. We take the first row, first column in both of them and write it in the first row, first column. We take the first row, second column, and we have a 2 plus 6, and that goes into the first row, second column, etc. So now that we just add up these guys together, we get 6, 8, 10, and 12. And this is it. This is just the resulting matrix to this. It's a very easy addition, and it works the same way for subtraction as well. So if this was a minus 6, this would be 2 minus 6. We would have minus 4 instead of an 8 here, for example. So addition is really one of the simplest ways. Just make sure you have two matrices of the same dimensions and just add elements on the same position. Now, move on to multiplication or, well, division. Let's start with multiplication of a scalar with a matrix. We're not going to learn division because usually just multiply or multiply to a fraction, so it's the same thing. Just like addition and subtraction are here in this very example. But order is important, as we will see later. So let's just focus on the topic at hand. We remember scalar multiplication at vectors. So a vector times a scalar, we multiply each component with the scalar and get the result. This works because of unit vectors. Now let's rewrite this vector as a matrix and solve the result. So we get 2 here, this is here, and this is here. How would we get this? Well, we see that we can set the same rule as we did with the vectors, where each component, in this case, entry, is multiplied to the scalar. So one such example would be 3 times matrix of 3, 4, 7, and 8. We multiply 3 to each individual entry or element, and we get 3 times 3 is 9, 3 times 4 is 12, 3 times 7, 21, 3 times 8, 24. It's that simple. Now, to move on to harder topics, matrix times matrix multiplication. Let's suppose we have two matrices we want to multiply. One with dimensions of m by n, and the other one of n by p. The result will then be of m by p dimensions. Here we see two things. First one is that the first matrix must have the same number of columns as the second matrix has rows. both are n. And the final matrix will have the same number of rows as the first one, and columns as the second one. Now, this is all overcomplicated, so let's see it on an example. Let's say we have a 3 by 2 matrix and we're multiplying it by a 2 by 2 matrix. We see that n of the first one and n here are the same. So that means that m and p will just be taken from the original ones, like we see here. So the result will be a 3 by 2 matrix. If we had a 3 by 2 and a 2 by 3, these two are the same, so the resulting matrix would be 3 by 3. Kind of like that, if you want to help. So, but how does this even like work in practical sense? How do we even multiply stuff? Well, there are some explanations like rotate this 190 degrees to the right so you have the same height on both of them, and just like, I'm not gonna bother you with those. So let's check the theory here. We see that the product will have a weird combination of elements. If I were to explain the actual cause and reason for this, it would be a bit too complicated for what we will need them in the future. Plus, there's a ton of videos specifically on this subject, far better quality than what I could make, so yeah. I do promise to solve an example after this, so it's gonna be like a little bit easier to follow along, where this rule will be shown in the easiest way I possibly can, like really easy, so if this isn't clear, just skip it. So anyway, here we see that the position 1, 1, so first row, first column, will have A times E plus B times G. First row of the matrix would represent the x-coordinate, so in the result, it will be present in the x-coordinate as well. So if, let's say each of these matrices is built from vectors, so this first one is built out of vector 1 and vector 2, and this one out of vector 3 and vector 4, their x-coordinate is on top. So now, okay, technically here we have the y component of the vector of the second matrix here as well. That's because that's just how transformation works, because everything affects everything to some degree. So in the result, it will be present in the x-coordinate as well. So these two x-coordinates of transformation will be present in the x-coordinate of the result. And C and D are basically the y-coordinate space position, whatever you want to call it. So they will be present in the y-coordinate position for the result as well. Now we will just fill in the rest. So here on the right, I'm just drawing on the side. So A and B are the x-coordinates of the original transformation, if you want to help it like that. So they're going to be on the x-coordinate position in the result. Just like in addition, corresponding elements were only in their positions. Here is just the right direction in the right position, so like that. Now we will fill the rest of the matrix. We will follow the rule since column count of the first matrix must be equal to the row count of the second. An element from the second matrix's nth row will be matched to all elements from first matrix's nth column and be placed in the same column they were originally in. So long story short, we remember ij, I being column and j row. In each element, the second matrix will be positioned in the same j position and multiplied to all elements from the first matrix whose I positions are equal to the elements j. So example, second matrix element E, for instance, is in the first row, so I is 1. So it will stay in the first column, j is 1, and be multiplied to the other two first column values from first matrix, A and C, as their I positions are 1, which is equal to E's j position. I know this is a mess, but on the example, it's a lot easier to follow along because we have visual. I know that because I wrote it and I didn't just like edit this one, but maybe it has been a mistake. Same thing for G. Second row, first column element. So it shall remain in the first column because the column stays the same, and it will be multiplied to the second column values of the first matrix because it itself is in the second row. As to reinforce this idea, column number stays the same, multiplied to all values in the other matrix whose column number is the same as the numbers or values own row number. Now we have F, a second column, the first row, so it will stay in the second column and be multiplied to all other first column entries of the first matrix. And lastly, H, second row, second column, position in the second column, multiplied to all elements from the first matrix and its second column. And now I know this is hella complicated, so let's see a number example. I will show it, color-code it for help, give you some time to solve it, and then check the progress, okay? But here basically we see we get this formula. So this one times this one plus this one times this one. So we kind of have like this and this rule following for this one. And then for this one, we'll just have A, B, F, H. For this one, it's C, D, E, G. Kind of like this. You circle the row and then the columns, and then just like go element by element, kind of like that. But here for the actual example, we have a product of these two matrices, so you can pause to solve it, but I'll keep explaining how to solve it so we can know that basically if you want to follow along. So first things first, we know that the first element of the first row of A must be multiplied to the first element in the first column of B, and second element of first row of A with second element of first column of B, and the sum of them will represent the position of 1, 1 in the result. So basically, yeah, in the first matrix, so the one that's written first, rows are important, and in the second one, columns are. So like we can just say, we're gonna be only looking at rows, and here we're gonna be looking at columns. So first element is by default this one, second element is this one, and here first element is this one, second element is this one. So as we said before, we'll be looking at the first row first, because this is the first row element, and first column, of course, because we're looking at the... So A matrix defines the rows, and then B matrix defines the columns, so, or the other way around. So if this is the first row, first column of the product, we're going to be looking at the first row, first column. If we're looking at the second row, first column, we're looking at a second row in A and first column in B. So the position in the result is determined by the row count. So basically, if you know from which row you're taking from A and from which column in B, that position is there in the resulting matrix. I hope this kind of helps you out, because this is a really hard concept to grasp as a beginner, so I'm trying to like over-explain it several different ways, because yeah. But basically, I'll take the first value of the first row and multiply it to the first value of the first column and get this. I will add to it the second number in the first row and multiply that number to the second number in the first column to get this. Add it together, and since we're looking at the first row of A, we're looking at the first row of the result. Which column? First column in B, first column in the result. And I insert in value 19 as the result. I hope this is clear. And next, we are looking at the second row, first column, as I said before. So we're going to be looking at the second row, first column. Now we're looking first element, first element, first element, first element. Add to that second element here. Solve all of this and insert into the matrix. And we're halfway done. Next, we're looking for the first row, second column. So first row, second column. And we see that we have first element, 1, 6. And second element, 2, 8. Add it together, 22. Insert in the appropriate space. And we're there, 3/4 of the way. And for the last one, it's a second row, second column. We'll take the second row of A, second column of B, first element with the first element, second element, add those products together, and we get 50. So this is the result. Now, if I were to show the full screenshot of this exercise, we see that we can get the result of this 2x2 matrix multiplication, 2x2 with 2x2 matrix multiplication, with only 8 multiplication steps and 4 additions. It's relatively easy once you get this rule that in the first matrix you're looking at the rows and in the second one you're looking at the columns. This is like the only thing I would like. If you were to take anything from this lecture, it would be this, that multiplication of matrices. First one is important, the rows, and the second one is columns. This is also why you cannot switch them around, because for homework, if you want, switch these two matrices around and see if the product is the same. But yeah, now, to simplify that multiplication to a matrix times a vector, which is just a smaller matrix. When matrix is multiplied to a vector, the result will be a vector, since the matrix itself is an operation that transforms the vector. Because of that, the order in which we write them, as I just said, is important. First will be the matrix, which will act like a rule or transformation for whatever follows it. After that, there will be the vector on which we are performing the transformation, and the result must be a vector, since transformed vector. So let's write it all out and start solving. First, we have to make sure that the rule that n1 equals to m2 must be true, as we learned in the multiplication before. So the number of columns of the first one has to be equal to the number of rows of the second one. That is true. Now, this is taken care of, so we can multiply these together. So for instance, this is the general rule. We see that this one has 2 columns and this one has 2 rows. So we can multiply them together. And if we went back, we see that the product matrix, this rule follows again. We will be looking for positions of the resulting matrix by defining the rows of the first one. So the rows of the first one and the columns of the second one will define the position in the result. Since there's only 1 column in the second one, there will be only 1 column in the result. As we see on this here, the resulting matrix should be 2 by 1, because this and this value. So like this. This is kind of another connection we can use. And these guys will just define in which row the elements are written. So technically, we can just write them out as a second matrix A, C, E, and B, D, F. And now, since this one gets multiplied to the first element, because it's a first element, we're just going to be like A, G, C, G, E, G, and then this is the second element, and these are the second elements. So this is BH, DH, FH. And now we just add these together and we get the result. For our matrix, we have a 2 by 2 matrix, so slightly easier. So we'll have 2 rows and 1 column. So in the result, we will just take the first element, second element. So this is the first element and this is the second element. Sorry, like this and like this, I guess. And then the second row will be first element of the second row times first element of the first column, and then plus second element of the second row, and then the second element of the first column. Basically like that. And this would be the result. So if I erase all of the craziness that I was writing here, this is the formula for the result. Now, many textbooks will tell you to memorize the row and column rule, which I definitely think you should at least keep in mind, as it's not that complicated from the way I explained it like here. But to simplify it, vectors tell us how much of the x and y direction with its components we have, and the matrix tells us where those directions or components will move or transform to. So we're simply taking the transformed x direction, scale it by the x component of the vector, take the transformed y direction and scale it with the y component of the vector, and then add those two together. So you can kind of see that the first column of the matrix is connected to the transformation of the x component, and but it's present in both of the components of the vector. So basically all of this affects everything. That's why the next concept, the next slide, is the way it is. It's called an identity matrix. What even is this? Well, their whole point is basically that if you multiply it to another matrix, it will give the same matrix as we multiply it to as the result. Just like we're multiplying numbers with 1. And they're basically square matrices, or matrices that have the same m and n value, like 2 by 2, 3 by 3. And their elements are all zeros, except for their diagonal, which is filled with 1s. I kinda can't sketch, but okay. So first row, first column, second row, second column, all elements with coordinates where I and j are equal, those elements are present with 1. So we see from the rules of multiplication, multiplying this to any matrix that fits the criteria for multiplication gives us back the original matrix we're multiplying to. For instance, if we had a vector and we were like, okay, do the rule here, the result would be x times 1, so x plus 0y, because we're looking first element, second element in the first row. And then in the second row, we would have 0x plus 1y, and 0y is 0, 0x is 0. We're left with xy. So we see this is how an identity matrix works, because all other elements here are 0, so they're kind of like not influencing the coordinates outside of their respective positions, basically. So small jump back to when we multiplied a scalar with a vector to extend it. How would we rewrite that scalar as an operation or matrix that would achieve the same? Well, change the 1 to a 2 in an identity matrix, basically. Why? Well, you can multiply them to each other if you want, but it's basically like multiplication with extra steps, or to avoid using scalars, you can use a matrix and write it something like this. So instead of using 2 times a vector to get this, you can just multiply 2 to the identity matrix and get 2, 0, 0, 2, like here. And basically just multiply this matrix to this vector, and we get this as the resulting vector. So this is a matrix whose transformation is defined as doubling both coordinates. So double the x coordinate and double the y coordinate. This is a bad symbol, I'm just going to use a dot. Basically like this. Voila! As easy as that. Now, a question for you. What would matrix 3001 do? Well, let's write out the process. So first, I'm marking the rows again and the columns, so I can always keep that handy. And I'm going to be like, okay, first element, it's 3 times 3, plus second element is 0 times 4. And then first element, second row, times first element is 0 times 3, plus second element is 1 times 4. This is 9 plus 0, and this is 0 plus 4. So we're having 9 and 4. And we see that our final vector is 9, 4. So this matrix right here just extends the x component to 3 times its original value, but keeps the y value the same. That's why the matrices are better than scalars, because they allow for more precise manipulation with vector components. Along with rotation, of course, which are the other components, because, well, they affect... this one affects x as well, this one affects y as well, whatever. So they cause rotation, I think. But I won't cover that much, because it's even up to now maybe a lot of information, maybe it's too much for some of you. So I'm just going to try to keep it to the basics. So now we see that multiplying matrices together is basically combining transformations into one operation. So think of like automation, for instance. Instead of having 3 separate machines do the job and have people carry the products between them and manually starting each process, we connect the machines together with like a conveyor belt or something, set it so they run in certain order, allowing for input of raw material and getting out, for example, separated, cleaned, and maybe even color-coded crystals if we take mineral separation as an example. So basically just like combining multiple steps into one step. And this also explains why the order matters, because let's take painting, for example. Let's say you want to paint a nice mountain view with a house in front of the hills and then a person up close. So the image is comprised of 3 parts. First is the mountains, second is the house that's somewhere here, and then is the person who's standing right in front. So each element slightly overlaps the previous ones. If we say we're drawing the entirety of the image, so everything that this person is, we just draw, and then everything this house is, we just draw, and the entire sky and background of the mountains, it makes sense that first we would put the mountains, then the house, and then the human. Why? Because if we start with the human, the mountains will overlap it. If we start with the mountains and then the human and then the house will be in front of the human, which doesn't make sense because the house would just be floating in the middle of the air, like a piece of dirt on the camera lens, for instance. So basically, the steps are important. Again, assuming you don't paint around stuff, so like you would start with a house and then paint the hills around it, and then the grass around it, and then the person in front of it. That kind of is, but if we're imagining this as the entirety, so we draw the entire background, and then the intermediate step, or whatever the decoration is, and then the foreground. Just like they did the painting with the good old days, basically. And now for the last 2 topics. First is determinants, not to be confused with discriminants, that we had in quadratic equations. So basically every square matrix, so matrices like 2 by 2 or 3 by 3, they have a determinant. But what does that mean? Well, determinant tells us the area. But which area could there be? Well, let's take a 2 by 2 matrix, for example. We can imagine that each column represents a vector. So vector 1 would be AC, and vector B would be BD. So this could be the graphical representation, for example, one of many. Now, we could add these two vectors, let's say a different representation, with a parallelogram rule, just like the image shows. And, oh yeah, as we can see, the sign to show that something is a matrix is in square brackets, but to denote something is a determinant, you use straight lines, basically as if you're taking the absolute value of the number arrangement like we see here. I'm gonna show it on the next slide, so don't worry, but basically we're using the parallelogram rule to add up two vectors. So we get this as the sum of the sum vector, basically. And yes, you mark the determinant of matrix A that equals to the surface as absolute value of the number arrangement. So this is true for matrices like 2 by 2, 3 by 3, etc. But this rule for 2 by 2 tells us the surface. For a 3 by 3 matrix, we would have a volume of a box. Of course, it can be negative too if the right values are too big or even negative. Now, what is the formula? Pretty simple for 2 by 2 matrices. It's AD minus BC. So technically, we draw a diagonal line in here in the matrix from A to D and C to B, and then we just connect them. Now, however way you want to remember it, you add the products of the numbers there. So A times D is one product and C times B is the second product. And then because the slope of BC is going from left upwards, or maybe another interpretation is it's falling to the left, because like we can imagine both of these falling. And if it's falling to the left, the sign will be negative. If it's falling to the right, the sign will be positive. So A times D has a plus sign because it's falling to the right, and BC has a minus sign because it's falling to the left. So whichever way you want to remember it, we just multiply the slope with a minus to get it into the right direction. But yeah, so our formula for the surface of, basically for the determinant of the matrix A would be A times D minus B times C. So what would be the determinant of this matrix? Well, let's write down the formula. AD minus BC. Okay, sure, but how do we know which one is which? Because we could easily have a matrix AC BD, where it's like in this order downwards, which is not standard, but it could happen. So the coordinates in the matrix are opposite for the 2 by 2. So if we have only 1 and 2, so 1, 2, and 1, 2 for rows and columns, it's like binary system. So if we have an element of 1, 1, we're flipping both of these coordinates to get a 2, 2. And if we have a 2, 1, we flip both of them, so 2 becomes a 1 and 1 becomes a 2, and we have 1, 2. Kind of like this. This is only useful for 2 by 2 matrices, because 3 by 3 gets significantly bit more complex. But yeah, basically like that. So we will have these two elements multiplied together and added, or to add to that, we will add a negative value of these two elements added together. So basically 2 times 4 minus 3 times 1, and that equals to 8 minus 3. Oh, I forgot to... Am I dumb? Slightly. Yes, I forgot. Ignore this. The next slide is kind of... I forgot to add a minus 3. So the result is 5. I kind of forgot to add the rest of the math here. Also, instead of coloring it green, I probably colored it black. Happens, okay. So this is the result, because we have 2 times 4 is 8 minus 3. So 2 by 2 matrices are quite simple in this regard, but a 3 by 3 matrix might cause some issues, so I will have it more or less as an honorable mention. So I know if I wrote it by hand, it would be a mess, but this is a wonderful show on how to find it. So you have your matrix, which I have circled on the right. And you basically write the same matrix on the side. So we have 2, 1, 3 as the matrix, and then 2, 1, 3, minus 1, 6. But technically we don't need the last column, but let's keep it simple. So we will refer to this original part as the matrix and this as the copy. This is not the official terminology, but it might help imagining it. After that, you will draw the diagonals from up to down, like the red ones on the image, and from down up like on the blue one, so over the central line here. So the first three elements, so all in the original matrix, we start in the, basically for each element in the first and the last row, we're gonna draw a diagonal all the way down. So it has three elements in it. That way we have the three red lines diagonals from top for these three elements and three blue ones to the right up for these bottom row elements. Basically just like this. Basically we're only originating from the elements of the first matrix and extending it into the second matrix or for the first diagonal of the first matrix, but whatever. That's why we drew the duplicate on the right, so we can actually extend it logically. Of course, you could also just do the pattern recognition like this, and this, and these are the three diagonals. Yes, but whatever is easier for you. For me, it's actually this one on the left, but for beginners, it's this one. Actually, everyone uses this one as far as I know. This is just like my personal preference for some delusional reason. But yes, the copy is in the yellow filled one, and the original one is in the yellow empty one. Now, all the lines that go from left to right down will be positive, so the red ones. And all that going from the right up to left bottom are negative. So imagine, as I said before, imagine the direction. If it's towards the left falling, it's negative. If it's falling to the right, it's positive. Kind of like that. Kind of like directions from chemical reactions, I guess. Now, we were gonna be multiplying the elements. So let's take the first diagonal. We have 2, minus 2, and 6. We're gonna multiply all of them together and add a plus in front, because it's a positive direction. Move on to the second diagonal. We have a 1, minus 5, and a plus in front, because it's positive direction. Third set is 3 times 2 times 4, or 3 times 4 times 2, and a plus, because it's a positive direction. Now for the first blue one, we have a 3, minus 2, and minus 5, and a minus, because it's in the negative direction. We have a 2, minus 1, and 2, and the negative direction, so minus. And then 1, 4, and 6, and minus, because it's in the negative direction, because it's falling to the left. All of that added together, so multiply and then add, we get minus 45. The sign here tells us whether the coordinate system is in counterclockwise orientation, which is told by the positive determinant. But if it's negative like here, then the system is clockwise. But don't worry about this at all. This is not something that's crucial to us at all, at least for the foreseeable future, which is at least 2 years. Now, we can use matrices and determinants to help us solve all problems, like system of equations, or overcomplicate them. For instance, let's say we have two equations like these. Now, I know these two are easy and we can solve it the fast way, but we can also solve it using today's lecture. First, we need to get the numbers out of these equations. Well, the coefficients multiplied with the variables. So that's 1, 1, 5 for the first one, and 2, minus 1, 1 for the second one. We will write one matrix with the coefficients that were in front of the variables, then a vector with coordinates of x and y, and a resulting vector with components that are equal to the results of the equations. So like this. The coefficients are here in this matrix. The vector or the variables are here, and the results are here. Now, for the matrix on the left, the determinant of it, if it's 0, there is either no solution or infinitely many. If the determinant is anything else but a 0, we have one solution. So technically 1 times minus 1 is minus 1, and then minus 1 times 2 is 2, that's minus 3, I think. That seems about right. So this is not 0, so we have one solution for x and 1 for y. And yeah, now you could be given a problem written like this, and it reads in the exercise that if you transform an unknown vector with the given matrix, you will get a vector 5, 1, and you must find the original vector for the task to be complete. So you write out the matrix times the unknown vector that equals to the new one, and from that you get a linear equation we see on top. How? Well, by multiplying. Well, technically it could just be like, yeah. So we remember the R rules, so I'm just gonna put it back here in case you forgot. And write out here, so 1 times x plus 1 times y, 2 times x minus 1y, And that equals to, so the first row will be equal to the first equation and the second row to the second equation. It's literally that easy. So you write it out, solve for x and y from these two, because this is a lot easier, trust me. There is a way to solve using the matrix multiplication, but I've checked that math, and that isn't the goal of this lecture. It's a bit more complicated than I wanted it to. There is a lot more about matrices, but I think this is a good start and basic explanation to allow you to build fundamentals and then decide whether you want to study more on your own. So here is the mini test to finish off today's lecture and the math chapter. So thank you so much for everyone tuning in. The next video will be a physics map roadmap, so how the physics lecture will be in order. I will be more loose on the definition than I was on math, because on math I set pretty high standards for myself with defined lectures and defined goals. However, for physics, I'll just go over the chapters and then the concepts we will cover. As for the order, I'll try to make sure that everything is covered, and if some things deserve more time or less time, I will adjust appropriately so I don't have to do any last-second corrections like I did here when I realized that I was dumb and I put something too hard too early on. So thank you so much for tuning into today's lecture. I hope you're doing amazing. I hope everything went well, and I'll see you all on our physics next quest. Bye!